Still laying the foundation for stochastic processes, this third video considers classification of stochastic processes. We've seen bits of these ideas previously. Classification of stochastic processes. A stochastic process is a collection of random variables indexed by time, or you can say it is a system that evolves over time with some randomness, right? So it describes how a random system evolves. Mathematically, you have collection of all x of t such that t belongs to t, where x of t is a random variable representing the state of the system at time t, while t is the set of time indices. So examples of stochastic processes include stock price movement, number of customers arriving at a store, population growth, noise in communication systems, temperature variations. So we talk about the main classification of stochastic processes now. Stochastic processes are clearly classified based on two properties. So we classify stochastic processes based on time index and the state space. These produce four major types of processes. You have, for the time type, you have discrete time. For the state type, you have the discrete state. An example of that is random walk, right? So if discrete time, discrete state, you have random walk. Discrete time, continuous state, you have AR models. Then continuous time, discrete state, you have like a Poisson process. And then you have continuous time, continuous state, you have Brownian motion. So you can have a discrete time, discrete state stochastic process, a discrete time continuous state, continuous. So you can have discrete, discrete, discrete continuous, continuous discrete, and continuous continuous, talking about time and state now. So we now study each classification systematically. So let's start with the discrete time stochastic process. So for the discrete time stochastic process, so a discrete time stochastic process evolves only at specific time steps. So the time index set is t, which is 0, 1, 2, 3, and all that. So the process is written as x naught, x1, x2, x3, all the way down. And examples of this will include daily stock prices. So stock price on January 1st, stock price on January 2nd, stock price on January 3rd. Of course, another way to look at stock price is, oh, what has the stock price been from, I mean, every minute of the day, Then you have daily stock price, you have yearly rainfall, you have number of customers per hour, you have weekly sales at each time step. So the time step can be daily, yearly, hourly, or weekly, or secondly, or minutely, whatever you want to choose. So at each time step, the system moves to a new random state, right? So we go on to and that's a very good example of stochastic process also is radioactive decay because it has a half-life. After every half-life, the uh after the half-life, right, the radioactive substance becomes halved, right? So a random walk is a classic discrete. So for an example of what you have considered is a random walk, which is a classic discrete time stochastic process. It is defined as xn, which is equal to xn minus 1 plus zn, where zn is plus 1 with probability 0.5, and zn is equal to minus 1 with probability 0.5. That's the random part, right? This means that at each step, the process moves either 1 unit up or 1 unit down with equal probability. If x naught is equal to 0, then the position evolves randomly over time. And we have that represented right here. And so if you have 200 time steps now, this is the kind of thing you have. So it goes up, it comes down, with the same probability like that. Uh, so if I run it again, as you already know, it keeps giving us so it keeps changing, right? So this is running now. So once it finishes, it's going to change. So you see it has changed again. Okay, so I run it again, changes again, I run again, it keeps changing. So because it is stochastic in nature. So then we go on to talk about continuous time stochastic process. So a continuous time stochastic process evolves over continuous time. It is written as x of t and t is greater than or equal to 0. So t, you cannot, in the unlike the case of the discrete where you can say time 0, time 1, time 2, here the time it just keeps moving. So from time 0 all the way until you want to stop. So here time can take any real value, not just integers. So in a discrete system, the time takes integer values, but here it takes real values. So examples include stock price movement. There's daily stock price, that is discrete, but stock price movement talks about, you know, continuous movement of the stock. So it's more like you just get into the system at any point in time and you see where it is going to. Then you have radioactive decay, internet traffic, temperature changes. Continuous time processes are widely used in physics, finance, and engineering. So a very good example of that would be the Poisson process. So a Poisson process models random arrivals over time. So let n of t represent the number of events that occur by time t. So the probability distribution is p of n of t equals k, which is equal to lambda t raised power k e raised power minus lambda t of k all over k factorial, where lambda is the average arrival rate, t is time interval, and k is the number of arrivals. So properties of a Poisson process include the fact that at time 0, the number of arrivals is 0. Then you have independent increments and you have stationary increments also. So, and we have this represented by this interesting looking plot here. So, but of course, because it is a stochastic process, if I run it again, the shape might change, it tends to change from time to time. So you can see some changes happening here and there, you know. So you have the time, you have the number of events happening in those times. So this is a Poisson process. Now let's talk about discrete. So we've seen discrete time, right? We've seen discrete time, we've seen discrete state, we've seen discrete time, continuous time. Now let's look at a discrete state stochastic process. So discrete state stochastic processes. So a discrete state process takes values from a countable set. So the value is from the countable set, not the time this time around. It is the value itself coming from a countable set. So that imagine we have a discrete state process takes value from a countable set. Example state space will be S. The other time it was time, which was 0, 1, 2, 3. Now it is the state itself, not the time, because it's now discrete state. So for discrete time, time is 0, 1, 2, 3. But for discrete state, the space is 0, 1, 2, 3. So examples include number of customers in a queue, numbers of failures in a system, number of infected individuals in a population. So you remember during COVID, maybe day 1, 0 people infected, day 2, maybe 1 person infected, day 3, you have 5, and then it keeps going like that. Okay, so that's discrete state stochastic process. So these states are integers or countable categories. So, and a very good example of that is the Markov chain. So a Markov chain is a discrete state stochastic process. So the key property is the Markov property, that the probability that something is happening at a point, given that it had happened at a point earlier and all the points before it, is equal to probability that x of n plus 1, probability that something is happening now, given that it has happened exactly before now. So this means that the future state depends only on the current state, not on past states. Okay, so where I'm at now is determined by my previous state, and where I will be in after now is determined by where I am at this point in time. That is the whole Markov property. So a Markov chain is described using the transition matrix. What's the probability with which I'm going to move? Okay, like imagine you have 3 states now. So what's the probability? I think I need to demonstrate. Can this graph show me here? Okay. Okay. Yeah. I'm just going to do, of course, you discover that along this line, everything is adding up to 1. So across the rows, everything adds up to 1. So, or let me just, okay, I guess I can snip this to demonstrate what I want to do. Yeah, that's a better way to go. Yes, I'll do a new one rectangularly. So, okay, so I can copy. and take it here. So I can paste it right here. Now, see what I'm talking about. Imagine that this is state one, two, three, state one, two, three. So the 0.6 means the probability of moving from state one to remain at state one, that's 0.6. Probability of moving from state one to state two is 0.4. Moving from state one to state three is zero. Probability of moving from state two to state one is 0.3. Probability of remaining at state two is 0.5. Probability of moving from state two to state three is 0.2. And lastly, now you have the probability of moving from state one to three to one, that's zero. Probability of moving to state three to two is 0.4. Probability of remaining at state three is 0.6. That's what this whole thing means. So, and that is used for a Markov chain. So each row represents probabilities of moving from one state to another, and that's what I've demonstrated right there. And of course, when we run this code, you see we have 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 2, 2, 2, and it keeps going. So if I run it again, it just changes. So these are all integers now, like that, all integers. So let's talk about continuous state stochastic processes. So a continuous state stochastic process can take any real value. The state space is S equals minus infinity to infinity. So you have stock prices, temperature, interest rates, and noise signals. These processes are commonly used in finance, physics, and signal processing. Interestingly, I have a playlist on spectral analysis, which basically deals with signal processing, right? So in that case, now you can see a state as a signal, like that. So Brownian motion is one of the most important continuous time, continuous state processes. So it satisfies W of zero, which is zero, independent increments, normally distributed increment. The increment distribution is W of t minus W of s, which is normally distributed with mean zero and standard deviation t minus s. This process is used to model particle motion in physics, financial asset prices, and diffusion processes, like that. So you have the Brownian motion here. Of course, you have a Brownian motion in 500 time steps. So we can keep, if you keep running it, it keeps changing. Keep running, it keeps changing. Now it has changed again, changed again, changed again, changed again. It's Brownian motion for you. Continuous time, continuous state, uh, stochastic process right there. Continuous time, continuous state. Okay, now we look at the combined classification of stochastic processes. So like we said, if you have for the random walk now, the time type is discrete, the state type is discrete, that's random walk. For AR models, the time step is discrete, the state type is continuous. For Poisson process, continuous time, discrete state. Brownian motion, continuous time, continuous state. Understanding this classification helps determine the mathematical tools required, the appropriate modeling technique, and simulation methods. So you have a worked example here. Of course, we are still going to talk about queuing theory in some depth later, so not to worry. So imagine customers arrive at a store according to a Poisson process with rate lambda equals 4. So equals cost 4 customers per hour, right? Find the probability that 3 customers arrive in 1 hour. So the solution using the Poisson distribution formula, you have lambda t raised by k raised to minus lambda t over k factorial. Here, lambda is 4, that's the arrival rate. 4 customers come in an hour, and t is 1, that's t for 1 hour, and k is 3. So we want to check what's the probability that 3 customers are going to come within that hour. So you just fix them. That's probability n equals 3. That's equal to lambda is 4. T is 1. That's 4 times 1, 4. K is 3. E raised by minus lambda is 4 times t, which is 1 again. So e raised by minus 4 all over 3 factorial. That's 64. E raised by minus 4 over 6. Probably numerically, the probability that n is equal to 3 is approximately 0.195. So there's a 19.5% probability chance that that 3 customers will arrive in 1 hour. So that's pretty low. Okay. So we can also use we can use Python code to verify that. So you have arrival rate to be 4, and you are considering the possibility of 3 people arriving in 1 hour, and then you just use the Poisson formula right here and print your result, which is still 0.1953 and all that. So in summary, we see that a stochastic process is a set of random variables evolving over time. So a set of random variables evolving over time, or you can say it is a system which evolves over time with randomness. So the two main classification criteria are time index and state space. So four major categories arise. You have the discrete time, discrete state, stochastic process. You have the discrete time, continuous time stochastic process. You have the continuous time, discrete state stochastic process, and you have the continuous time, continuous state stochastic process. These classifications help determine how the process is analyzed and modeled in statistics, engineering, and finance. So that brings us to our practice problems, where we have to solve the following problems related to the classification of stochastic processes. We have some conceptual questions. Define a stochastic process and explain the meaning of the notation x of t. Because it's just a random variable, uh, you know, indexed by time. Stochastic processes are random variables indexed by time, basically. So explain the difference between a discrete time continuous process and a continuous time continuous process. Of course, it's about the time. So you have discrete time steps here, integers, and you have continuous time steps here that can take real values, real number values. Then explain the difference between a discrete state process. Of course, the state is discrete. The continuous state, the state is can take a real value. So classify the following processes as the following process as discrete time or continuous time. The daily closing price of a stock. The daily closing price of a stock. Of course, that's discrete time because it is the closing price, not the evolution of the price. It's the closing price. So classify the following process as a discrete or continuous. The number of customers in a queue at a bank. You want to classify as discrete state or continuous state. That should be discrete, of course, that's discrete. Then give two real-world values of continuous time stochastic processes and give two real-world values of discrete state stochastic processes. We've seen all of that previously. Then we have some identification problems. For each of the following, identify whether the process is discrete time or continuous time, discrete state or continuous state. The number of emails received by a person each hour. So that feels like the arrival stuff. So that should be like what we considered just now. So Poisson process, that's continuous time, discrete states. That's continuous time, discrete states. Then the temperature recorded every minute. Of course, that's so every minute. So that is actually the temperature itself is the state is continuous, but the time is discrete because it is every minute. So the state is continuous, so it is discrete time, continuous state. Then the number of cars passing through a toll booth by time t. By time t, that's so time t, number of cars, that's discrete state, but the time t is continuous time. Then the position of a particle undergoing Brownian motion. Of course, for Brownian motion, um Brownian motion, where does Brownian motion fall again? I think it is continuous, continuous. Yeah, Brownian motion is continuous, continuous. So it is continuous time, continuous state. Then the number of defective items produced in each batch. That batching talks about discrete time. Defective items also is discrete. So that's discrete time, discrete state. Then we talk about classification problems. Consider the process Xn representing the results of the nth coin toss. 0 is tail, 1 is head. Classify the time index and the state space. So that looks like discrete time, discrete space to me. Then 14, let x of t represent the amount of rainfall accumulated up to time t. Accumulated up to time t. So it's not up at particular time points. So in that case, to classify the time index and the state space now. So it is rainfall accumulated. The space is definitely continuous, and then the time is also continuous. Yeah. Let n of t represent the number of customers arriving at a store by time t. What type of stochastic process is this? Number of customers arriving at a store by time t. That's like the Poisson thing. Uh, Number of customers arriving. So Poisson, that's basically the Poisson process, which is continuous time, discrete state. Continuous time, discrete state. That's what that should be. A discrete space state because of number of customers. Time t is discrete. I mean, it's continuous rather. So discrete, continuous time, discrete state. The process records the daily temperature in a city. Of course, daily temperature in a city is that daily thing talks about discrete time. Then temperature, the temperature is actually continuous. So discrete time, continuous state. The mathematical practice, now, Poisson process has rates. Lambda is 3 events per hour. Find the probability that exactly 2 events occur in 1 hour. So we just do the kind of thing we did now. Now lambda is 3 and k is 2. So we have all that. Yeah, so try your hands on this. Let's see how well you can get this gist. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel, I thank you very much for doing that. If you haven't subscribed, question is why not? Go ahead right now and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel. That way you can get to see some videos first, or you're the only one to see some videos as members of the channel. We can hang out together to discuss whatever interests you on my channel. You can request of PDF copies of my notes. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.